So this is continuation of our discussion on the topology and geometry of different regions in plane. Now, to discuss further regions, we are going to need the concept of a curve. Now, what is a curve? So intuitively speaking, we can say that a curve is a thread on a flat plane or a string stretched in a flat plane. Now, if we want to define it precisely, then we are going to need the following definition. So a curve is basically a function z of t which is equal to with two components x of t and y of t. And if we want to write it down involving this complex notation iota, then this is x of t plus iota y of t. Now in this case, x of t is a function of one variable, y of t is a function of one variable. In fact, this t is known as the parameter of this curve. And this t varies from the point A to the point B. So if we choose different values of this parameter t, then we get different points. And when we join these points, we will get geometrically what we will get is a curve, a thread in the plane. Now, we want to impose one further condition on this curve. We want to impose that these curves should be continuous. So the thread stretched on the plane should not be broken. So it should be connected all the way. So in other words, we can say that x of t and y of t should be continuous real valued functions. And how to check the continuity? Because these are functions of one variable, so we can use our knowledge from calculus of function of real numbers to check that whether these x of t and y of t are continuous real valued functions or not. Now this curve C has z of t as parameterization. Now let's consider some examples. So starting from this function z1 of t which is equal to 6 cosine t plus iota 6 sine t, where t varies from 0 to 2 pi. So as I said earlier, to get the points on the curve C1, we need to vary the values of t. Now let's start from t is equal to 0. So when we put t is equal to 0, we can see that we are going to get, so sine 0 is 0 and cosine 0 is 1. So the answer is going to be 6 plus iota 0. So in other words, this is the point where t is equal to 0. And similarly, when we take other values of t, we are going to get other values. So let's just take a jump and take t is equal to pi by 2. So at pi by 2, sine pi by 2 is 1, but cosine pi by 2 is 0. So what we are going to get is 6, iota 6. So in other words, this point is basically the point where t is equal to pi by 2. Now let's take another jump and take t is equal to pi. Now at t is equal to pi, once again this sine pi is 0 but cosine pi is minus 1. So we are at the negative side, and this is the value when t is equal to pi. And when we take t is equal to 3 pi by 2, then we will get this point and up to so on. Now when we vary t from 0 to 2 pi, we are traveling. Okay, so we are traveling in this direction, and if we join all these points, then we are going to get a circle. Okay, so we are moving in this direction. So we can say that a curve defined in this parametric way gives us more than a geometrical shape. Okay, so a geometrical shape is just a circle, but it is also giving me the direction in which we are moving. So when we start from t is equal to 0, we get different points on the circle, and when we move on, we get more points on the circle, and when we take t is equal to 2 pi, we arrive back at the same point. So we travel in this direction. So this is the orientation of our travel along the curve. Now let's consider another example of C2. Now in this case, we have 6 cosine t minus iota 6 sine t, and the variation of t is the same, 0 to 2 pi. Now if we want to sketch this curve, we start from t is equal to 0. When we put t is equal to 0, we are going to get 6. Okay, so this is the value when t is equal to 0. And when we take t is equal to pi by 2, then in this case, cosine pi by 2 is 0, but sine pi by 2 is of course 1, but the answer is minus 6 iota. So in other words, this is the value for t is equal to pi by 2. And similarly, we can observe that when t is equal to pi, we are going to get this value, and when t is equal to 3 pi by 2, then we are going to get this value. And when we join these points, we are going to again get a circle. But now the circle, of course, in the previous example we also got the circle, and in this example we also have a circle. But what is the difference between these two examples? So in that example we were traveling anti-clockwise, and in this example we are traveling clockwise direction. If a curve is given, then when we vary the parameter t, we are traveling along the curve. And of course, when t is equal to a, we have this initial point, and when t is equal to b, we have the terminal point on the curve. And if the initial point and the terminal point of the curve are same, then we say that the curve is closed. Now let's consider this example. So in this example, we observe that this is basically a circle where the initial point and the final points are same. Okay, so this is a closed curve. Now let's consider another example and try to observe if it is a closed curve or not. Now in this case, the function z of t is given as 2t plus iota 3t, where t is the parameter and the variation of the parameter is from 0 to 1. Now let's first sketch this curve, and then we will see if it is a closed curve or not. When t is equal to 0, the value is basically 0, 0. So this is the point when t is equal to 0. Now when t is equal to 1, the output is going to be 2 plus 3 iota. So in other words, we are going to get this point. So this is the point when t is equal to 1. Now since it's a continuous function, 2t is a continuous function of t, 3t is a continuous function of t, so there is going to be no break when we are traveling from t is equal to 0 to t is equal to 1. And if we take other points in between these 2 points and join them, then we are going to get the following line segment. So the graph or the geometrical shape that this z of t function is representing is basically a line segment. And as we can see that this is the point z of 0 and this is the point z of 1, and z of 0 is not equal to z of 1. So we can say that it is not a closed curve. A curve is called a simple curve if it does not cross itself. Okay? So in other words, if I have a curve which is a circle, then we can easily see that it is not crossing itself, so it is a simple curve. And if I have a curve like this, now we can see that at this point the curve is crossing itself. Okay, so in other words, we can say that when we are traveling, let's say this is our starting point. Okay, so this is our starting point, and if we, let's say, travel in this direction, and when we are traveling from this way and we reach at this point, let's say this point is z of t1. Okay, now we travel, we move on, the parameter of t is increasing and we are traveling along the curve. But when we are traveling and we are coming back to the same point, so in other words, this point is also represented by some other value of the parameter t2. So this point is z of t1 as well as z of t2, and then we go back to our initial point. So what does this represent? So this represents that a curve is not simple if it is not one-to-one. So what is a one-to-one function? So in this case, why it is not one-to-one? Because we have z of t1 is equal to z of t2, but t1 is not equal to t2. So for two different inputs, t1 and t2, we are getting the same output, which is z of t1, which is equal to z of t2. So we can say that a curve is simple if the function defining that curve, which is z of t, the parameterization of the curve, is one-to-one. Okay, so in other words, z of t1 is equal to z of t2 implies t1 is equal to t2. If this condition holds, then we say that the curve is simple. Now let's consider some examples. Okay, now this line segment, of course, is simple but not closed. Similarly, this parabola is simple but not closed. Now let's consider another example. Now this example, the curve is intersecting itself, so not simple and not closed. And in another example, it is an incomplete circle, so not closed but simple. Let's consider another example. In this example, it is simple as well as closed. Moving on to another example. Now this is closed but definitely not simple because it is crossing itself. Now in this example, it is simple as well as closed. Moving on to our last example. In this case, we can see that it is simple as well as closed. Now, we have observed that a curve which is defined by a parameterization function z of t, when the parameter t increases, then we are traveling along the curve. And if it is a simple closed curve, then this simple closed curve enclosed an area in the complex plane. So for example, if it's a circle, then this circle enclosed the following area in the complex plane. Similarly, any other simple closed curve is going to enclose some area in the complex plane. And we also know that if a function z of t, the parameterization is given, then it is also going to give me an orientation in which I'll be traveling along the curve. Okay, so there will be some orientation of the curve as well. Now, if I'm traveling along the curve and if the area enclosed by the curve is always on my left side, then we say that this curve is positively oriented. Okay, so in this case, we can see that when we are traveling along the circle, then the area enclosed by the circle is on the left side. Okay, so we are traveling along this thing and it is always on the left side. Similarly, in this case, when we are traveling in this direction, of course, in this case, if we want to check if it is positively oriented or not, we need to have a direction in which the object is moving along the curve. Okay, so in this case, we can observe that the area enclosed by the curve is always on the left side. So it is positively oriented. It is positively oriented. But if we consider another example of a circle where we are moving in the clockwise direction. Now in this case, the area enclosed by the circle is on the right of the object moving along this curve. Okay, so we are moving along this circle, but the area enclosed is on the right side. Okay, so we can say that it is not positively oriented. Now, how do we make sure that there is always going to be an area enclosed by a simple closed curve? Now, this is guaranteed by the Jordan curve theorem. Now, we are not going into details of this theorem. And of course, the proof of this theorem is beyond the scope of this course. But we have a guarantee that a simple closed curve is always going to enclose an area in the complex plane. So we can always check that whether a simple closed curve is positively oriented or not. Now let's continue with our next definition. So this is another property of a region in the complex plane. Now a region or a set, subset of a complex plane is connected if for every pair of points there is a curve joining them which is entirely contained in S. So for example, if I have the following set S, then if I choose any 2 points in this set S, then there is always going to be a curve joining them, and this curve is also contained in the set S. But if I take another example of a set S2, and this set S is given by 2 different components. Okay, so let's call this component A, let's call this component B, and this union of A and B gives me S2. So this S2 is basically A union B. Now let's see if this set S2 is connected or not. So let's choose a point Z1 in the component A and point Z2 in the component B. Now there is a curve in the complex plane joining Z1 and Z2, but this curve is not entirely contained in the set S2. So we can say that the set S2 is not a connected set. Now let's consider another example where we are considering this annulus. So annulus is basically defined by this condition. Okay, so what does this condition give us? What is the geometrical shape of this region? So the condition is the modulus of this z should be less than 2. So the distance of this complex number should be strictly less than 2. So it's a kind of open circle of radius 2. Okay, so this is 2. And the boundary, of course, is not included, and everything inside this circle is included. But the modulus should be strictly greater than 1. So in other words, the distance of this complex number from the origin should be strictly greater than 1. So nothing inside this small circle is included. So everything inside between these two circles is included. So this is the annulus. Now if we take any 2 points, so let's say this is the point z1, this is the point z2. Now there is always a curve joining them, and this curve is also completely contained in this set A. So we can say that the annulus is an example of a connected set. Now let's move on to our next type of region in the complex plane, a domain. A connected open set is called a domain. So we have two conditions. A region is a domain if it is connected as well as open. Now let's consider this example of half plane. Okay, so consider this complex plane. Now what is this set H? So set of all complex number whose real part is strictly greater than 0. So in other words, everything on this side. And of course, nothing on this imaginary axis is included because the real part is strictly greater than 0. Now we can easily see that it is connected because any 2 points can be joined by a curve, and this curve will be completely contained in this region. And also it is open because the boundary is not included, or we can say that corresponding to every point we can always find an epsilon neighborhood which is completely contained in this set. So we can say that this half plane is an example of a domain. Now the next property of a region is boundedness. Now we say that a region is bounded if we can find a closed disk which completely contain that set S. So for example, if this is the set S, we can easily find a closed disk containing that set S. So this is bounded. And of course, if we consider the entire this half plane, then this is not an example of a bounded because there does not exist a closed disk completely containing this region. Now let's consider another example. Now consider all those complex numbers where the real part lies between 1 and 2. Okay, so what is the geometry of this region? So the real part should be strictly greater than 1 and not equal to 1. So that's why I'm taking this dotted line. This is 1. And similarly, it should be strictly less than 2 and not equal to 2. So that's why I'm taking this dotted line. So this is our region. And we can easily see that this region cannot be enclosed inside a closed disk. So that's why this region is not bounded. And if we consider this open disk, then definitely this open disk is a bounded set. Now in this discussion, we learned about curves, closed curves, simple curves, orientation of curves, and we used the definition of curve to define what is a connected set. We also defined what is a domain and boundedness of a set. Now these definitions are basic definitions, and these are going to help us in exploring different properties of complex functions which we are going to define in our future discussions.